Hi everyone, this is Mrs. J, and today we're going to be solving logarithmic equations, but first please pause the video and give this warm-up a try. Alright, so here we're using combinations of our product, quotient, and power properties to condense. So first, if you have an exponent, we're going to need to, or a coefficient, we're going to need to move that value up to the exponent spot. And here, if you have the sum of two logarithms with the same base, we can condense them using our product property. And here, again, we'll start with our power property to move our coefficients. And then if you have a difference of two logarithms with the same base, here we both have natural log, which is base e, we can condense them using our quotient property. So these properties are going to be tools that we may need to use today when we're solving logarithmic equations. All right, so today we're going to be solving logarithmic equations. And depending on how your equation looks, we're going to use one of two methods. First, if you ever have an equation where you just have two logarithms with the same base that are equal to each other, well, just by logic, if the two logarithms are equal and the bases are equal, the insides of the logarithm must also be equal. So if you have log base b of x equals log base b of y, by logic, x must equal y. So you will be able to solve some of your equations just using simple logic. You just set the insides equal to each other. But sometimes we are going to need to use this alternative method. So for this method, we're going to isolate our logarithmic term just like we do with most different types of equations. We isolate first, and then we're going to rewrite our equation in exponential form, which will allow us to solve. Now, sometimes in order for us to fully isolate, we will need to first condense our logarithms using those properties that we just reviewed in the warm-up. And then last but not least, something extremely important for these, we do need to check our solutions for any logarithmic equation because logarithmic functions have domain restrictions. And if a function has a domain restriction, we will see extraneous solutions when we're solving those types of equations. So we have to check our solutions every single time. All right, let's give a couple of these a try together. So here I have the natural log of 4x minus 7 equals the natural log of x plus 5. So since I have a single natural log equal to a single natural log, the bases are the same, they're both base e, I know just using logic that the insides of my logarithm must also be equal. So I can solve this equation simply by setting the insides equal to each other. So I'll just subtract x from both sides and add 7 to both sides. And dividing by 3 on both sides gives me x equals 4, but of course we need to show our double check. So we're going to substitute. So I have 4 times 4 minus 7 equals the natural log of 4 plus 5. Here, well, we have 16 minus 7, which is 9, and 4 plus 5, which is 9. And the natural log of 9 is equal to the natural log of 9. So we have a true statement, which means our answer is valid. All right, let's look at this next one. Log base 2 of 3x minus 6 equals log base 2 of 9. Again, logarithm equal to logarithm, base is equal to the base. So the insides should be equal to each other. So again, just say 3x minus 6 equals 9, 3x equals 15, x equals 5. Let's do a quick little check on the side. Log base 2 of 3 times 5 minus 6 equals log base 2 of 9. 15 minus 6 is 9. So log base 2 of 9 equals log base 2 of 9. So that has verified that our solution is correct. All right, go ahead and pause the video and give this one a try on your own. All right, so here we have two base 10 logarithms. These are common logs equal to each other. So the insides must be equal based on logic. We get x equals 2, and a quick little double check will confirm our answer. All right, let's try a couple more together. Here we have log base 2 of 5x minus 17 equals 3. So here we just have a single logarithmic expression. So for this type of equation, we will first try to isolate. Our logarithmic expression is already isolated. So our next step is to rewrite. So remember, logarithms define exponents. So this logarithm is saying take this base, raise it to this power, and this is your result. So we can say 2 to the power of 3 equals 5x minus 17. In rewriting, you can see now that we've freed up our variable. Our variable was trapped inside our logarithm, but when we rewrite it in exponential form, now it's no longer trapped, and I can solve. So we know that 2 cubed is 8, and then this will allow us to finish solving. We have 25 equals 5x, so x equals 5, but first, before I box my answer, let's check by substituting into the original equation. So we have 5 times 5 minus 17 equals 3. Log base 2 of 8 equals 3. And here I know that log base 2 of 8 is equal to 3. So 3 equals 3. So x equals 5 is a solution. All right, down here, again, our logarithmic expression is already isolated, so now it's time to rewrite. So I'll say 3 to the power of 4 equals 10x minus 9. So that's rewriting in exponential form. And then we know that 3 to the power of 4 is 81. And if I add 9 to both sides and divide both sides by 10, I get x equals 9. But first, let's check. So we have log base 3 of 10 times 9 minus 9 equals 4. So log base 3 of 81 equals 4. And 3 to what power equals 81? 3 to the power of 4. So 4 equals 4. So x equals 9 is a solution. So again, make sure your logarithmic expression is isolated, and then simply rewrite in exponential form and finish solving. All right, go ahead and pause the video and give this one a try on your own. Okay, go ahead and check your work. Our logarithmic term is isolated, so I can rewrite into exponential form by saying 2 to the power of 5 equals x minus 6. 2 to the 5th is 32, and we get x equals 38. Here's my double check. Log base 2 of 32 is 5, so our answer is valid. All right, so now we're going to try one together that's a little bit trickier. The reason why this is trickier is because we have 2 logarithms and an extra constant. So I can't just set one logarithm equal to the other because of this constant. So in order for me to fully isolate, I am going to need to condense these 2 logarithms into one. So luckily, they both have the same base. They're both common logs. So I can condense them into one using our product property. So it'll be the common log of 2x times x minus 5 equals 2. Now within that logarithm, let's distribute. So we have 2x squared minus 10x equals 2. Now from here, I'm ready to rewrite in exponential form. We don't usually write this, but a common log has a base of 10. So if I were to rewrite this, it'd be 10 to the power of 2 equals 2x squared minus 10x. So let's write that out. And now here you can see that we have a quadratic equation. So for any quadratic, the first thing I will do is set my equation equal to 0. So we have 0 equals 2x squared minus 10x minus 100. Here, let's try dividing both sides by 2 to simplify our equation a little bit. And if you can, when we're solving a quadratic, of course, factoring is the way to go if it is factorable. So what multiplies to make negative 50 and adds to make negative 5? Well, we have negative 10 and positive 5. So x minus 10 times x plus 5. And with a little zero product property, we can finish solving. Okay, so we have two potential answers. But I say potential because we need to check. So let's start by checking x equals 10. So we have the common log of 2 times 10 plus the common log of 10 minus 5 equals 2. So here, this gives us the common log of 20 plus the common log of 5 equals 2. I'm going to condense these using my product property. The common log of 20 times 5, which is the common log of 100. And 10 to what power makes 100? 2. So this logarithm is equal to 2. So we get a valid true statement. So x equals 10 is a solution. But I still need to check x equals negative 5. So let's plug it in. We have common log of 2 times negative 5 plus the common log of negative 5 minus 5 equals 2. So right off the bat, we have an issue, actually in both of our logarithms. Here, we have the log of a negative number. Remember, we're starting with base 10 and we're raising it to a power. There's no way to take a positive base, raise it to a power, and get a negative number. So anytime you see a negative number within a logarithm, that is an undefined value, and it means that that x value is an extraneous solution. So it turns out that x equals negative 5 is not a solution. So we only have one solution, which is x equals 10. So remember, the inside of a logarithm can never be negative. All right, here's one more for you to try on your own, so please pause the video and give it a shot. Right, go ahead and check your work here. The first thing that I did is I condensed my two logarithms using the product property. And then I rewrote in exponential form. 4 to the power of 3 is x squared plus 12x. So here we have a quadratic equation. Once you get down to the quadratic equation, you should feel pretty confident here because we just set it equal to 0 and then we either factor, or if you need to, you could also do the quadratic formula. So here negative 16 gives us an extraneous solution because we get a negative inside our logarithm, but positive 4 gives us a valid solution. So this is our only answer. All right, we're going to try one more problem together. So this is a logarithmic equation, but it is a natural log. So here we're going to provide an exact answer and a decimal approximation rounded to the nearest hundredth. So you can see that our logarithm is fully isolated. But when we go to rewrite in exponential form, I want to remind you that a natural log is just log with a base of e. We don't typically rewrite it like this. We'll usually write it like this, but if it helps you to rewrite it, you can always do that. So we have e to the power of 3 equals x minus 7. And then we can finish solving for x by adding 7 to both sides. Now I know this is going to look a little strange, but e to the power of 3 plus 7 will be our answer, and it would be the exact answer. Okay, before I get the decimal approximation for that, let's check our answer. Really, we just want to make sure we don't have a negative inside our logarithm. So we have the natural log of e cubed plus 7 minus 7 equals 3. So the plus 7 minus 7 will disappear. So natural log of e cubed. Remember here, I have base e, they essentially undo each other, and all I'm left with is 3. So 3 equals 3. So we know that it is a solution. Now that we have verified that it is a solution, we're also asked to give a decimal approximation. So your scientific calculator should know this has an E button. It's right above the ln, the natural log button. So you have to hit second ln, which gives you e to the power of 3. Make sure you close your parentheses and then do plus 7. And we should get approximately 27.09 if you round to the nearest hundredths, which is 2 decimal places. So again, when you have a natural log equation, you will get, most of the time, you will get an answer with E in it, and that's okay. Looks a little bit strange, but this is exact, and if you needed to, you could always plug that into your calculator to get a decimal approximation. All right, that is all for today's video. Thank you so much for watching.